Thank you, Keith, for the introduction. Video streaming is popular with many applications that are known by us, like YouTube, Netflix, and Hulu. It is reported that 1/3 of all online activity is spent watching videos. And Americans spend 3 hours and 9 minutes a day on average streaming digital media. And according to Cisco annual internet report, there is a significant demand for the bandwidth of video ranging from tens to hundreds of megabytes per second. And more importantly, the bandwidth needs grows exponentially because the demands of the video dimension increases recently. And since video codec is a key component that makes video delivery through the internet in a compact format, it is a very crucial component nowadays. So video codecs, it has a very long history. For traditional video codecs, its history dates back to 1988, when the codec of H.261 was first developed. And it's still evolving, that in 2020, the codec of H.266 was developed. And where are we? Here, H.264 is a codec that is used by YouTube for people to upload their videos. And AV1 is used by Netflix. And in parallel to that, learned video codecs that are built from deep neural networks, using deep neural networks to do encoding and decoding, are emerging. In 2018, there is a codec reported to be compatible with H.264. And just in last year, there's a codec that is reported to exist, VVC, that's the most state-of-the-art traditional video codec. The performance on learning-based video codecs are amazing. And clearly, there's a trend that learner video codecs are rising. So the question that we ask is, can learner codecs replace traditional ones? So to verify this idea, I conducted a pilot study. So in this study, compare two learned video codecs, DVC and RVC, with two traditional video codecs, H.264 and H.265, with different presets. And the learner codecs will be running on GPU, while the traditional video codecs will be running on CPU. And let's look at coding efficiency. So what is coding efficiency? It's basically a trade-off between bits per pixel, the video is compressed, and the video quality in terms of signal-to-noise ratio, PSNR. And from this graph, we can basically see that traditional video codecs are not as good as learning-based video codecs. Learning-based video codecs, they are closer to the left and top and have a better coding efficiency. However, if we look at the decoding speed of learning video codecs, they do not look so good. They can barely achieve 30 frames per second. And compared to the traditional video codecs, the traditional codecs can easily achieve over 120 frames per second, even on a CPU. So the answer to this question is not quite. So let's dig into the reason of slow decoding. So here's a pipeline that is adopted by most learned video codecs to do video coding. So first, they will have a frame that will be independently encoded or decoded. Based on this frame, there will be multiple frames that will be encoded or decoded dependent on the previous frame, the adjacent frame. And to clarify, here I only simplify the reference of frames, but actually in practice, if you are familiar with video coding, there are B frames, but eventually the I and P frames are most fundamental in video coding. And the insights that we derive from this paper can actually be applicable to the B frames. So that's why in this talk, I will mainly focus on the I and P frames. That is like a structure shown in this figure. And this way of frame referencing is defined by tight frame referencing in this paper. And there are some problems. So deep neural networks, they are notorious for slow decoding speed or slow processing speed. So it takes time to process each frame, and it takes a long, long time to process a long sequence of frames. And that creates a gap that between the slow decode, the deep neural networks, and the real-time frame rate needs. So our intuition is that, why don't we just use non-adjacent frames as a reference? So like shown in figure here, how about we use the first frame as the reference for the third frame? And we define this as loose frame referencing. And there are actually two benefits. So first, in terms of coding efficiency, temporary closed frames, they are similar. Like the frame in the first position and the second position, they are similar. And so in this way, there may not be much difference when they are used for frame reference. So they might not affect the coding efficiency very much. If we look at the decoding speed, loose dependency allows parallelism. It allows frames at the second and third position to be processed in parallel, and parallelism potentially improves the speed. And our work is based on this idea to use loose frame referencing, and there are several challenges I will talk about in today's talk. The first question we answer is, how do we schedule frame processing? The second, how do we design learn the codec? And last, how do we adapt the streaming infrastructure for learning-based video codecs? Now let's first look at the first problem. So frame processing basically is a problem that you have an input of a set of video frames. Your design space is you could design which frame should reference which frame. You design a reference relation between them. And you optimize two objectives, the coding efficiency and decoding speed. I know here we have a lot of concepts, but I will make it simple. So I will abstract this problem into a graph traversal problem. In this graph traversal problem, you will treat each vertex as a frame indexed by 0, and 1, and 2. And the reference relation will be defined by the directed edges between the vertices. And in this graph traversal problem, you are trying to start from the independent encoded frame to progressively visit all the other frames. And in this process, you need to optimize two objectives. The first one is the sum of the cost of the edges. And the second is the number of iterations for you to iterate this whole graph. And if you can iterate it with less iteration, it means better parallelism improves the speed. So let me show two examples how graph traversal can be treated as frame processing. So for tight frame referencing, you process frames in this way, from 0 to 6. And let's see the reference cost. Between 0 and 1, the cost is 1. Between 1 and 2, the cost is still 1. And if we sum them together, we got a reference cost of 6. Now let's look at the reference depth. You can notice that it took 6 iterations to reach the last frame. So reference depth quite high, it's 6. And it will cost a slow decoding speed. If we look at an aggressive way using loose frame referencing, that we start from one frame, and we reference this frame to encode or decode all other frames. In this way, we will have a reference cost between 1 and 0, there will be 1. But between 2 and 0, there will be 2. And if we add them together, we got a quite a high reference cost of 21. The good news is the reference depth is quite small because we only need one iteration to visit all these frames. So this is a coding inefficient scheme. And facing these two schemes, we are asking, can we achieve something in between? And this points us to the decision of using a binary tree. So a binary tree like this, the frames will be referenced from the parent to its children. So in this way, compared to aggressive loose frame referencing, the reference cost is not that high. And if we look at the reference depth of the binary tree increases logarithmically with the number of vertices. However, the reference depth in the tight frame referencing increases linearly with the number of frames. So the binary tree is the core idea of this paper. And based on this binary tree, we can consider the next problem. How should a codec be designed? So first, with this binary tree, we want to minimize the reference cost. So what we do is that we solve a minimal spanning tree problem. I will not go into that detail, but here's the result. How should friends be organized in a binary tree? And if you're still following my presentation, you might notice there's a problem with this binary tree. That's the difference between friend 0 and 4, friend 1 and 3, friend 4 and 6. The reference cost is greater than 1, and this makes it a poor decision than tight friend referencing, in which the reference cost is consistently 1. So this will cause our algorithm to have a low coding efficiency. So to address this problem, let's first look at how the friends process and see if we can find any insights from it. So we will first process friend at 0, and we process friend 1 and 4, and then the friend at the last level of this binary tree. And these 2 friends will be processed in parallel. These 4 friends will be parallel. And this actually presents an opportunity that we exploit the inter-friend correlation between the friends at the same level of this binary tree. In terms of exploring the inter-friend correlation, there are actually a rich body of literature in the machine learning community. And in this paper, we employ the most famous one when this work was developed, called self-attention mechanism. And to spare your time, I will not go into detail of how I divide the friend information into motion and residual and how I transform the convolutional neural networks. You can look at detail in my paper. Now, let's look at the last problem. So actually, this is a problem for almost all learning-based video codecs. So to understand this problem, let's understand how video on demand works. So video on demand, it has a video downloader. The video downloader will download video from the content distribution network. The video will be decoded and be saved in the buffer for the viewer's view. There is an IBR algorithm that will choose the bitrate level based on the buffer. If the buffer level is high, then we will have the ABR algorithm probably choose the high bitrate level. But if the buffer rate level is slightly lower, it might choose a bitrate that is not that high to be a little bit conservative. The problem with learning-based video codecs, the decoder is very slow. So it will limit the speed that the buffer level increases. As a result, we will constantly get a very, very low buffer level. And that makes the ABR algorithm think, oh, the network is poor, and we should choose just a very, very, very low bitrate. And this presents our opportunity to improve the ABR algorithm. And what we did is that we proposed a virtual buffer that captures the content in the buffer and like existing ABR algorithm, but it also captures the content that are downloaded but not decoded yet. And this prevents the ABR algorithm to be conservative. Now, here is the evaluation. So in the evaluation, we consider a setup where the media server stores multiple videos. These videos will be requested by a client. The client using an ABR algorithm to request and download video segments. The network is emulated with 1,000 traces collected under true network conditions. We use a QE metric of the weighted sum of video quality and the negation of rebuffer rate. Let's first see the result with a slightly limited network bandwidth. So the left 3 methods are learning-based methods, and the right 6 methods are traditional methods. And we can generally see a trend that learning-based methods improve with the hardware. But overall, our algorithm is better than learning-based and traditional ones. There's a slightly better advantage of our algorithm against the learning-based approaches. That is because existing learning approach, they perform extremely poor when the hardware is not that good. But our algorithm can deal with that. And if we look at performance with better bandwidth, we can see the performance against the traditional methods actually improved. The reason is that there's a special property of learning-based video codecs that they can achieve better coding efficiency when the size of video chunks increases. Now, let me show some results of the QoE breakdown. That's actually unexpected when we are developing this work. So in terms of video quality, we see that LiFteR does not always achieve the best video quality. The reason is the virtual buffer, it will cause that slow decoding will get a very high virtual buffer, and that will cause it to choose a higher quality. And as a result, the slowest algorithm RLVC will choose the highest quality. If you look at rebuffer rate, LiFteR improves the rebuffer rate of existing learning-based ones, but not as good as existing traditional ones. There's also a slight glitch of LiFteR's rebuffer rate. That is a downside actually from parallel processing. Because when the network is bad, the video processor needs to wait for the frames to arrive. And if we use the parallel processing, it needs to wait more times. And that makes this rebuffer rate unstable. And here I want to summarize this work by the lessons I learned when I'm experimenting with learning-based video codecs. The first is tight frame referencing may not be necessary. And that's why this paper is exploring the possibility of a binary tree. The second, the codec should be co-designed with the frame processing pipeline. And that's why we are experimenting with the self-attention mechanism. And lastly, there's still room to improving existing infrastructure for the codecs. And what we did is we adapted the ABI algorithm. And that's the end of the slide. And I'm happy to take any questions.